Boys and girls, today you're going to do lesson 9-6, which is divide whole numbers and unit fractions. So we've basically already done this last week with doing that whole keep, change, flip thing. So that's our algorithm, and I'm going to review that, but I'm also going to add a model to it. Okay, I added a model when you did whole numbers divided by fractions, but I'm going to also show you a model, an area model, and a number line when doing a fraction divided by a whole number. So let's review. So I'm going to start off with doing a whole number divided by a fraction. Okay, so let's say I had 6 divided by 1/5. Remember, we're going to use keep, change, flip. So I'm going to keep the 6. Okay, I'm going to change the sign from division to multiplication. So I'm going to put the C for change. And I'm going to flip this fraction to its reciprocal or its opposite. Okay. But before I do that, remember, for fractions, we really can't divide a whole number by a fraction. We really have to multiply a fraction times a fraction. So for fractions to play nicely together, there have to be 2 fractions instead of a whole number and a fraction. So I'm going to take this, I'm going to keep this 6, but put it over 1, because remember, 6 over 1, if I divide 1 into 6, I get 6. So 6 over 1 is the same as 6. I'm going to change my division sign to multiplication, and I'm going to flip this fraction to its reciprocal. So instead of having 1/5, I'm going to flip it to its reciprocal or its opposite, which is 5 over 1. Then I'm just going to multiply my numerators together. 6 times 5 is 30. Over 1 times 1 is 1. 30 over 1, that's an improper fraction. Can't leave it, so I'm going to divide 1 into 30. And 1 goes into 30 30 times, because if I multiply it back, 30 times 1 is 30. So let's do a little model to show that. So let's say I had 6 candy bars. And I cut them into fifths, okay, or 5 parts. And let me just make these look a little bit more like they're all the same size. Point of fractions. Okay, so I'm cutting them into fifths. To make fifths, we know we're going to put 4 lines. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And 1, 2, 3, 4. So when I do the algorithm, 6 divided by a fifth, my answer ends up being 30. And sure enough, if I have 6 candy bars and I cut them into fifths or 5 parts, I end up with 30 pieces altogether, because I have 1, 2, 3, 4, 5, 10, 15, 20, 25, 30. Let's try another one. Again, I'm going to do a whole number divided by a fraction. Okay, so let's say I had 3 divided by a third. Okay, so again, I'm going to practice that algorithm of keep, change, flip. I'm going to keep the 3, but I'm going to put it over 1, because I really am going to end up doing a fraction times a fraction. And fractions only play nicely together if they're working with other fractions, not with whole numbers. So, and we know 3 over 1 is the same as 3. I'm going to keep the 3, but put it over 1, change the sign from division to multiplication, and I'm going to flip this fraction 1/3 to its inverse, which is 3 over 1. Then I'm just going to multiply my numerators, or the tops of my fractions. 3 times 3 is 9. Over 1 times 1 is 1. And just like 3 over 1 is equal to 3, 9 over 1 is equal to 9. But I'll divide it out. Doing the inverse of division here, because this is an improper fraction, I'm going to use multiplication. So 1 goes into 9 times, multiplying it back. 9 times 1 is 9. So my answer here is 9. And to show it, again, let's say I had my 3 candy bars. And I cut them into thirds or 3 parts. So I'm going to put 2 lines. If I want to make 3 pieces, I put 2 lines. 1 less line for how many pieces I want. So I should end up with 9 pieces here altogether, okay? So 1, 2, 3, 4, 5, 6, 7, 8, 9. So my model is matching my algorithm. Let's try one more like this. Let's say 5 divided by a half. Okay, again, I'm going to do keep, change, flip. I'm going to keep the 5, but put it over 1, because 5 over 1 is the same as 5. change my sign to its inverse of division is multiplication. And I'm going to flip this fraction to its reciprocal. So instead of 1 over 2, I'm going to have 2 over 1. Then I'm going to multiply my numerators together. 5 times 2 is 10 over my denominators or bottoms of my fractions. 1 times 1 is 1. 10 over 1, just like 5 over 1 is the same as 5. 10 over 1 is 10. But I'll prove it. This is an improper fraction, so I'm going to divide 1 into 10. Goes 10 times. I'm going to prove that by doing the inverse of multiplication, which is the inverse of division, which is multiplication. So 10 times 1 is 10. So my answer here is 10. And if I wanted to do, let's say pizzas, 5 pizzas, but I'm cutting them into halves or 2 parts, I should end up with 10 pieces altogether, or 10 slices. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So my model matches my algorithm. Okay, I'm also going to show you, so that was dividing a whole number by a fraction. But we've also practiced this week, the week we just passed, a fraction divided by a whole number. But we didn't look at it with models to match. So let's take a look at some models to go with it. I'm going to model it with a number line and also with an area model. So let's try 1/2 divided by 4. Same thing, we're going to practice that algorithm first, okay, which we've already done, so it's a little review. So I'm going to keep the fraction, change the sign, and I'm going to give the inverse of the whole number. So I'm going to flip this. So I'm going to keep my 1/2 and bring it down. I'm going to change division to multiplication. And we know 4 over 4. Again, we can't divide a whole number by a fraction or a fraction divided by a whole number. We have to multiply, and we have to multiply fractions times fractions. So we're going to have to make this whole number look like a fraction. So we're going to start it off being over 1. But because I'm going to flip it to its reciprocal, the reciprocal of 4 over 1 is 1 over 4. When I multiply it, I'm going to follow my normal algorithm. 1 times 1 is 1. 2 times 4 is 8. So my answer is 1/8. But let's take a look at that as a model. So let's say I have a rectangle. I cut it in half. And I shade one side of it. There's my half. But then I'm multiplying it by 1/4. So that means, vertically I cut this down the middle and I made halves. So now horizontally I have to make fourths. So I'm going to put 1/4 up here. And I'm going to cut this into fourths by putting 3 lines. 1, 2, 3. So now I've made 1/4, 2/4, 3/4, 4/4. I've cut this into fourths. And I want to dot 1 full fourth. So I'm going to put 1 dot across 1/4. I'm going to put a dot. And sure enough, if I look, my model is matching my algorithm because how many pieces do I have all together? 1, 2, 3, 4, 5, 6, 7, 8. And how many of them have shading and dots on them? 1 of them. So my answer is 1/8. I can also show that on a number line. Okay, so let's say I made a number line and I started it, and let's say 1 hole is here, and here's 2. Well, I can take the 1 hole and cut it in half. So here's a half, and here's 0 halves, and 1 is technically 2 halves. Okay, and then if I do that, to model the same thing, I can cut these halves into 4 parts. So if I do that, I'm going to put 3 lines. So if I look all together, I have 1, 2, 3, 4, 5, 6, 7, 8 pieces. Okay, so again, I've made eighths. Each one of these has now become eighths. This would be 0/8, 1/8, 2/8, 3/8, 4/8, 5/8, 6/8, 7/8, and 8/8, or 1 whole. Okay, so basically, again, my number line matches my answer to my algorithm. Let's try another one. Let's say I did 1/5 divided by 2. So 1/5 divided by 2. So again, I'm going to roll with that keep, change, flip as my algorithm. I'm going to keep the 1/5, change the sign to multiplication. 2 is the same as 2 over 1, and I'm going to flip it to its reciprocal, which was 1 over 2. Multiply my numerators. 1 times 1 is 1. 5 times 2 is 10. So my answer is 1/10. And I'll know, I should have mentioned this on the first example, but I'll know my answer is right, because if I'm taking something like a fifth, which isn't even one whole yet, and then I'm cutting the fifths in half, my answer should be getting smaller. And a half is smaller than a fifth or a half. Because remember, what I'm really doing here is I have a tiny piece, and I'm taking a tiny piece of a tiny piece. So my answer should be getting even tinier or smaller. And remember, we'll know this is correct also because bigger the number, smaller the denominator. Bigger the number, smaller the piece. Well, let's take a look at an area model to match this. So again, if I have a rectangle and I cut it into fifths, I put in 4 lines and I shade in one of them. Actually, I'm going to make this a little bigger just so you can see. So I cut it into fifths by putting 4 lines. I've got 1, 2, 3, 4, 5 pieces. So now I shade in one of them. So there's 1/5. But now I've got to multiply it by a half. So I've got to put a half here and cut this whole thing in half. Well now, and I'm going to dot 1/2. Because again, if I shade it in 1/5, I have to dot, or I have to shade going the other way, but I'd rather dot so you could see the difference. So here I'm dotting in 1 out of the 2 pieces I made, going horizontally. And sure enough, 1/5 times a half is 1/10. Well, sure enough, how many pieces do I have here altogether? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The denominator is always my total. And then how many pieces up here, if you see in your model, have both shading and a dot? 1. 1 out of 10. So my answer is 1/10. Also going to show it on a number line. So again, let's say I said here's 0/5, 1/5, 2/5, 3/5, 4/5, 5/5, which is the same as 1 whole. Okay? Well, I'm basically taking each of those fifths and I'm cutting them in half. So to cut them in half, I'm going to use 1 line. Well, now how many pieces do I have altogether? Well, let's look. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I've made tenths out of this by cutting my fifths in half. So this would be 0/10, 1/10, 2/10, 3/10, 4/10, 5/10 or half, 6/10, 7/10, 8/10, 9/10, and 10/10, which is the same as 1 whole. So I have 10 pieces here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So my answer matches my algorithm. Excuse me. My answer to my algorithm matches not only my area model, but my number line. Let's try one more. Okay, here we go. Let's do 1/4 divided by a third. I'm sorry, 1/4 divided by 3. So again, keep, change, flip. I'm going to keep the 1/4, change the sign from division to multiplication. This is really 3 over 1 because 3 is the same as 3 over 1. I'm going to flip it to its reciprocal, which is 1/3. Multiply my numerators. 1 times 1 is 1. Multiply my denominators. 4 times 3 is 12. Show it with an area model. I could cut this into fourths. Put 3 lines to do it. Shade in one of them. Then I'm going to put here's 1/4. Then I could go, so I cut these vertically into fourths. Now I'm going to cut the box into thirds. So I'll put 1/3. I'm going to put 2 lines to make thirds. And I'm going to dot 1 full third. So now, how many pieces do I have all together? Remember, my denominator is always my total. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So here's my 12. And how many pieces have how many pieces have both a dot and shading in it? 1 out of 12. And let's show it with a number line. So again, I could cut this number line into fourths. Here's 0 fourths, 1 fourth, 2 fourths, or a half, 3 fourths, and 4 fourths, which is the same as 1 whole. Okay. And then I'm cutting those into thirds. So that means I'm putting two lines to make thirds. Okay, so now altogether I should have 12 pieces. Let's check it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I'll mark them. Here's 1 12th. This was 0 12ths, 2 12ths, 3 12ths, 4 12ths, 5 12ths, 6 12ths, 7 12ths, 8 12ths, 9 12ths, 10 12ths, 11 12ths, and 12 12ths, which is the same as 1 whole. So this number line is matching my area model and my algorithm because I should have 12 pieces altogether. Now, by cutting the fourths into thirds, I've made 12 pieces altogether. I'll count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so I hope this helps for today's questions today, because some of them might ask you to, think of a model or use a model. You don't necessarily have to draw one, but you might want to think of one. You can draw one on the side to kind of help you to figure out the answers or to help you with the algorithm. So as always, I hope this helps, and good luck with your questions, and have a great day. Bye.